Yeah, it's 3 p.m. Welcome everyone to the first seminar in our Wolfram Technology web seminar series this year. This talk is about what's new in Wolfram Language 14.2. This session will be recorded, and I ask you to please ask your questions at the end of the session, where we'll have a quarter of an hour for answering any questions that may arise. Before we begin, let me just introduce myself and the company I work for. The company I work for is called 𝗪𝗵𝗂𝗵𝗂. We are a small company based in Perg in Upper Austria, which is close to Linz. We now have around 50 employees, which all more or less work in technical projects. We are a group of theoretical physicists, mathematicians, and software engineers, and of course some administrative personnel. And what is our relationship with Wolfram? We've been Wolfram technology reseller for more than 30 years now. We serve the German-speaking parts of Europe. That means Austria, Switzerland, and Germany. Among our biggest customers are the Austrian universities, which have a site license, and also the 𝗪𝗴𝗂𝗵𝗂𝗵𝗂 in Germany. We provide license and installation support for Wolfram technologies. And of course, we also do technical support for the different Wolfram technologies that exist. And we also have some our own Mathematica packages, like, for example, 𝗪𝗵𝗯𝗶₃ for financial risk management, which are based on Wolfram technologies. The topic of this session will have the following agenda. I've selected new features from the latest version 14.2, which I consider to be important for any kind of Mathematica user. We will start with a Wolfram Language 14.2 overview. Then we'll look at a new product which is called the Wolfram Notebook Assistant, which allows for using LLM modules in the Wolfram session. We will see what is new in the Wolfram core language. We will have a look at the changes in parallel computation. Then the major part of the talk will be about tabular data, which is the main feature of this new 14.2 release. And it's really, I would say, a great feature which finally enables you to work with big data in a Wolfram Mathematica session. Finally, we'll have a short look on the first steps into a new era, which is called GPU computation. And as I already mentioned, we will wrap everything up with a question session at the end of the talk. Let's get the Wolfram language overview. I really like this quote from Stephen Wolfram himself: "The drumbeat of releases continues." Wolfram has really now settled on having 2 major releases each year. And the first major release for this year is Wolfram Language 14.2, which was released in January 2025. And bug fix releases are only done if they are needed. And for version 14.2, just last week, we got a version 14.2.1, which contains a lot of bug fixes for the new version. 14.2 features 80 completely new functions from different areas, and more than 170 functions have been updated or extended. You probably have noticed that Wolfram language has moved away from the brand Mathematica in recent years, and now with version 14.1, it finally made the step to really rename the application as Wolfram app, which is indicated, for example, by the fact that is now seen as Wolfram here in the menu bar on the Mac. And the Mathematica brand remains, as we can see, for example, if we open the welcome screen here. But it's just there's no longer any technical exposure of that name. That means all the names in the file system and the application itself is now named Wolfram app. Yes. Let's get the uninteresting stuff out of the way first. What are the supported platforms of the new version? There has been very little change to the supported platforms. It's on the Windows side, it still supports Windows 10 and 11, and the Windows Server version 2019 or newer. On the Linux side of things, it supports the long-term support versions of Ubuntu from 2004 until 2404. And also it supports, for example, the Fedora versions, the latest two. On the Apple Macintosh, it has added support for the latest version of macOS, which is 15, and it also supports the 3 versions prior to that. There is also a free Raspberry Pi version of the Wolfram language available. This one is still at 14.1 because it always lags behind some months between the newly released version. But I think that 14.2 will be available soon on the Raspberry Pi as well. Let's now look at one of the most important features or most important releases from Wolfram in recent years, which is the so-called Wolfram Notebook Assistant. What is it? It's an all-in-one solution for using AI assistants in the Wolfram language. Let's just open the browser and go to the homepage of that product. What it essentially is, it's a new subscription on top of your existing Wolfram subscription, which lets you use large language models which have been curated by Wolfram themselves. That means there is no need for having additional accounts with other LLVM providers. And if we go to the settings here in the Wolfram preferences here, and I switch to AI settings here, there is this menu bar which lists all the available LLM providers. And here you find a new provider which is called Wolfram. And if you have a subscription like I happen to do, and I press the sign in button here, it will check my subscription status and say, okay, you have a Notebook Assistant and LLM Kit subscription. That means you can now use all this large language model functionality without having to have a direct subscription for one of these other services here. And how does this work? Let me just open a new notebook. And in the menu bar here, I have now this assistance section where I can simply press this icon here, and it gives me a so-called notebook assistant, which lets me interact with Wolfram's LLVM model with respect to the notebook that I see on the right side. If I press this sources button here, you'll see that. Let me just blow this up a little bit more. And also this one here. If you see here, this notebook assistant is connected to this untitled notebook here. That means all the inputs and outputs that are created in this notebook are visible to the large language model. And I can now, for example, ask the large language model an interesting question. What data have you been trained on? And ask the model. And it should then provide me the necessary information. Yeah, and you see that I've been trained on a diverse data set, publicly available information up to October 2023. And this includes text from books, websites, and sources. However, And the great thing, it has also been curated with a lot of Wolfram data that only Wolfram has. That means this model is capable of answering questions regarding the Wolfram language that the other models are probably not able to do in a similar quality. Let me just, for example, let's just say I want to plot a circle of spheres. I mean, why not? How am I going to do this? And then the model will now hopefully create a Wolfram code that does that. And you see it shows this code here. And I can now, for example, copy it to the clipboard or insert it directly into my working notebook on the right side and see what's happening. Yeah, okay. You see, this is already working Mathematica code, but it probably isn't what I expected, because this more looks like a bagel than a circle of spheres. But knowing about the sphere command, I know that there is for example, this has a radius, and if a simple put in a smaller radius here, it really then gives me what I wanted to see anyway. And this is very typical in working with any kind of large language model. The large language models gives you a solution that is 90% there or 95% there, but the final touches you have to do yourself because that's what, due to hallucinations and simply not having enough context, the output from the LLM model is never really exactly what you need. Another change in this version is that you probably remember this notion of a chat notebook from earlier versions. Chat notebooks and regular notebooks are really now the same, and you can simply, by pressing the quote key on your keyboard, you can simply insert a chat input cell into every notebook. And for example, if I can now really refine my graphics here, like for example, please increase the number of spheres, and it will create, or should create the correct mathematical code for that. It takes some time. Yeah, and what it did is just increase the step size here. And if I insert and evaluate the code, you see it looks much better now. And you see that, that the great thing about this, if you're like me, I have to switch between, I think, 20 programming languages nowadays, and I really don't have all these details in my head all the time. So working with an LLM model for creating the initial code or the initial sketch of code is really helpful and lets me finish the task that I have to solve in a much more efficient manner. Let's just close this thing here. Now, another feature of the Wolfram Notebook Assistance is the programmatic access to LLM functionality. What is meant by that? Mathematica 14.2 has integrated a new set of functions which all start with the prefix LLM, and all these functions let you interact programmatically with the LLM model. And you see this also the documentation notes that this requires access to LLM. This requires access to the LLM subscription. And let me just use this function now. Like for example, here I can put an input, create a short poem about programming languages, and it will then submit the code to an LLM model, and it then creates that the answer is then returned as a Wolfram language expression. Here it's just text, and you have a short poem here, which is probably not worthy of an award, but at least it's a poem. You can also, for example, create like Lambda functions. You create LLM functions where the parameters are actually submitted to an LLM model. For example, here I want an LLM function to simply describe the difference between two arguments. And what this gives me is an LLM function which takes two parameters. Yeah, I can then use this function simply under the name that is defined and say, please describe the difference between an apple and a pear. And it will go out and over the internet, it will call the Wolfram LLM service, which then will hopefully provide the necessary answer. And you see, you get an answer here. The answer can also be returned in a different format, like for example in a graphic, so you can immediately import it into some other form in order to programmatically work on the result. What's new in core language? It's fantastic that we always get new general purpose functions which are really useful. If you're experienced mathematical programmer, all of you have made the following mistake. You have a Mathematica function, like for example take, which calls a nested function, like for example import. And due to some circumstances, that the nested function fails because, for example, this import function fails because this CSV file that I was specifying is missing. And usually what you get is you get a cascade of messages here. This cascade of messages, and also in the final result is one where you have a partially evaluated expression where somewhere in the expression is $failed or $failure or $aborted in there. And now there's a new nice feature, which is failsafe. Failsafe is used to create safe versions of functions that can be applied to many inputs, quietly ignoring bad data. That means running the same input here with the failsafe modifier applied to the take function. It will return immediately $failed. How does this work? Failsafe will simply look at all the arguments to the function, and if any of the functions any of the arguments to the function is $failed, $aborted, $cancelled, failure, or missing, it will immediately return the result and unwrap it. I think this it's similar to how, for example, maybe monads or optionals work in functional programming languages, so that certain error messages are bubbled up until they reach the top. For example, when I apply the failsafe function to using the highlighted functions on highlight, you see that the highlighted function will only apply it to arguments which are not $aborted, $cancelled, failed, or failure or missing, and these will be returned as is. Another nice feature about failsafe is that let's, for example, say I want to use the square root function. But I also want to not let the result become complex. How can I do that? I say I define a failsafe function where I say please only apply the squared function to non-negative numbers. And that means if it now encounters a negative number, it will immediately abort with a failure and will not accidentally move into the complex space where I don't want to be. So much for failsafe. The select function, which is a very old function, has been revised in this version. It allows for returning certain properties now. For example, this is all this is how we notice it, the select function. I can specify a predicate here, and it will select from this list here the ones where this predicate applies. Like, for example, here I'm filtering the even numbers from the list of integers. What I can do now, I can use this rule-based syntax to specify which result I want to have. For example, this return the element is equivalent to the default version we always had, but I can now also make it return the index of the result instead of the results themselves. For example, the element in the second and in the fifth position, like 22 and 62, are actually the ones that I want that I get. Or I can even return a bit vector mask, which is an efficient representation of a list of booleans, which then, for example, can use for the pick function or something like that. And of course, this new select feature also works for associations, where I can, for example, put in the OR modifier, which will return all the results. It will return the element, the index, bit vector mask, and I can then use association map-based lookups to further process the result. A new function, which is also one which I really missed was missing for a long time, is the discard function. Discard is basically the opposite of select. That means instead of selecting elements from a list, it discards the elements for which a given criterion is true. Running on the same example as we did before, for example, instead of selecting the ones which are even, I'm discarding then all the arguments, and so that only the ones that are odd are left in the result list. And of course, it also supports all these features from the select function, like, for example, returning directly the elements, the index, the bit vector mask, and in the same fashion as select, it also works on associations. Another nice feature is the function association COMAP. In version 14.0, Wolfram Language introduced a function called COMAP. What does COMAP do? I mean, many times you want to run the same functions on the same data. Like, for example, in statistics, it's common to want to, for example, compute the minimum, the maximum, the mean, and the median at the same time. And you can do this with COMAP, where this function is then applied to the input here, and it will give you all the results as a list here. And association map is basically the same thing, but instead of returning the result as a list, it gives you an association where the key of the association is the function name itself. For example, here you see it's indexed by min, max, and so on. And this is very handily. For example, you can imagine like caching a lot of computations on the same data, and then using simply the function name, like for example, using median as the keyer and the lookup function for associations, in order to return the median of the random its. What's new in parallel computation? In parallel computation, there's really a great new feature. If you use parallel allocation often, you probably know that although parallel computation itself is really fast, launching parallel computations was really not that fast. And now what the parallel computation toolkit does, it does a parallel launching of kernels on remote machines. For example, on my local network, I have this a remote machine here, and I want to launch 8 kernels on that machine. And if I do that, you see that it returns almost immediately. That means it's almost independent of the number of kernels that you are going to launch on a remote machine now. And this allows for really large networks of Mathematica compute kernels. Then there is parallel table, which has been optimized for across multiple variables. Parallel table always was optimized for one argument, but now it's optimized for multiple variables. Like for example, here, if I want to compute the 𝗪𝗵𝗁𝗶 set, this is the famous Mendel function here, and I can use the parallel table function with 2 dimensions here in order to compute all the points. And this will then you will see that then it shows the progress here and the number of computations that need to be run. These are run now on my remote machine. And for example, I can then use arrayplot to plot the resulting Mendel set. Then there is parallel select and parallel cases, which are new. These, of course, are parallel versions of the single core versions we already know. Like for example, if you want to if you want to compute the prime numbers in the range until 10 million, if you do it with 1 core, it takes 2 seconds, and if you do it with parallel select, it will be much faster because it is able to run all the computations on multiple machines at the same time. The same is true for parallel cases, where the only difference is that instead of a predicate here, which is a lambda function, you here have actually a pattern which evaluates which is evaluated for cases. But other than that, it does the same thing. And if we compare here the single core case with the multiple core case as well, you see that we experience a similar speed up here. And this is really great because it's now much easier to really set up remote computations in an efficient way without having to wait for kernels to be launched for almost many minutes. Now let's focus on the most important topic of this new release, which is called tabular. And before we talk about tabular, let's talk about data science. What is data science actually? I've looked up the definition in Wikipedia, and the best definition I've found with is data science uses statistics, algorithms, visualization to extract knowledge from data. And interestingly, the term data science is much younger than Mathematica itself, because data science was invented, or the term was invented at the end of the last century. And you always could do more or less data science with Mathematica or the Wolfram language. What always was really good, Mathematica was really good at doing actually the actual computation on the data, the modeling, the transformation, the visualization. That always worked really well with Mathematica. What really wasn't always where you didn't have an optimal solution or experience was getting the data into the system. That means you had a data source like a database or a large CVS file, and you wanted to get the data into the Wolfram kernel. And due to some not high quality import functionality, it often was really cumbersome to get the data into the systems. And for example, we internally often really wrote the importers in a lower level language like C++ or Java themselves in order to get the data into the Wolfram session. And now with the tabular is now really a feature which makes this left side of things really much easier. I always like to look at new features from a historical perspective, because I've been using the Wolfram language now for more than 25 years. And if you have used the first versions of Mathematica, you probably know that in the first versions, a list was the only structuring element you had in order to describe data. Like, for example, let's just say we want to model data for persons consisting of a first name, last name, and birth date. What you would do, you would set up a vector of a heterogeneous vector where the first two elements are strings, which represent the first and the last name, and you would have a date list, which then represents the date of birth. And you would then use, for example, indices into that list in order to extract individual components of the record. Of course, if your record has hundreds of properties, this becomes very cumbersome and error-prone. And so another approach that was often used is the up-value-based approach, where you simply, instead of using a list, you created a new symbol, like, for example, your person symbol, and then use this person symbol as a type tag for the data, and you use the arguments for that function as the actual properties of a record. And this allowed for setting up transformation rules in the form of up values which could operate on that person object then. But in a similar fashion, you still had to use indices in order to extract properties from your data. Another approach which was popular at that time was simply using a rules-based approach, which has the advantage that the actual meta information, what the data is also contained in the data. Like, for example, you have set up rules where you say first name is John, last name is Doe, and so on. And you could then use this replace all operator in order to extract a certain property of the data object that you're working on. While this approach was very elegant, it had the drawback of being really slow, because this rule-based operation here is really a linear time operation which has to go through all the rule list. That means if you have many properties in your record, it will become really slow, very, very fast. And what Mathematica or what Wolfram gave us as an answer to these problems, it introduced with version 10 a new general type which is called association, which uses this syntax with these angle brackets here. And this is it introduced this syntax where you can directly use the key in order to look up properties of a record. And what also version 10 gave us was this date object, which enabled us to really represent dates by their own type, which made filtering for date and working with date and time to them much more easy, much more simple. And of course, if you could use the record, the normal function would simply then transform this association to a regular rule list. That means we can sum up that associations are an efficient representation of rule lists based on hash tables that allow for constant time lookup of keys. And that really has made working with data in the Mathematica session much simpler because these associations are really efficient. And what we also got with version 10 was dataset, where you could have then, of course, many records which are all structured in the same way and which then are wrapped in a datasets, which then gives you this nice representation. The problem with this approach of datasets is you see here that a lot of redundancy is contained here. That means all those records have the same keys and the same structure. And what dataset did not do, it did not optimize the internal representation of that data. And now with tabular, tabular is now the next answer in this everlasting question. Tabular is an efficient representation of a list of homogeneous associations based on in-memory column stores. What does that mean? I can, given the data set we have seen before, I can use this toTabular function in order to create a tabular from this data. And you see immediately that I can, for example, then get also a nice representation here where I can drag for example, the columns. I can increase it, and if there are many data, I can scroll through the representation of data. And of course, if I apply the normal function to my tabular, it will just return a list of associations. Where this is different is that if we compare the byte count of the data set, which is the original one from the last slide, the data set based one, with this new tabular based one, you see that even for this small amount of data, it already consumes much less data. And why is this the case? Because tabular keeps the schema of the data and the data itself separate. That means it only has to store the structure of data once, and if you add more data to your list of records, it will not consume any additional data for the structure itself, just for the records data that is added. And what is tabular? What tabular is less general than a data set because it requires homogeneous data. That means all the records in a tabular have to be structured in exactly the same way. They have to have the same keys, and then the number of keys must be the same. The data is stored in a column-oriented order, which makes it ideal for CPU caching and SIMD processing. That means in the data structure, all the different fields are laid out next to each other. And for example, if you run an operations like a find or something, they will be next to each other in the cache line, and this will help the processor to process the data in a much faster way. On top of that, the whole functionality that Wolfram provides for tabulars is enhanced by the Wolfram compiler. That means all the selects and the transformations that you do will actually run on compiled code, not on interpreted code. It supports efficient input from 19 formats, like for example, the most important ones are CVS and Excel, and also Parquet, which is probably a format you probably know if you work with big data, which is also a columnar storage format. It also supports out-of-core data. That means data where the actual data is not stored in the Mathematica session in the kernel, but resides in an external database. We will see an example of that later. But now let's now look at a really more complex example. I've prepared a set of Canadian postal codes here, which a file which I've found on my machine. And if you look at the file size of the machine, it's around 58 megabytes large. And if we print the first 5 lines of that file, you see that it's typical a CVS file, which starts with a header row, and then it continues with a number of data rows where each the data is actually the postal codes of the post offices in Canada, where you get the postal code, the city, the province code, city type, latitude, and longitude. And I can now use the new summary import feature, which lets me give a preview of the structure that Mathematica will use for that file. For example, for that file, the Wolfram language has detected that it has the following column types. Postcode ID is an integer 64, and the longitude and latitude are real coordinates, and the other data are strings. And before version 14.2, I would have to load this data as a data set into my session. And if I do that here, you see, although the import is quite fast, takes around 2 seconds. If I look at the byte count now, you see that these 76, almost close to 1 million records, take 1 gigabyte of main memory in my session. And that's really, that means I'm really restricted by the amount of memory that machine has here. And if I do the same input now as a tabular, simply putting in a tabular here as an argument, you see that the import itself is an order of a magnitude faster. And if I look at the byte count, it only takes about 17 megabytes to represent this data in memory now, which is a huge improvement over this 1 gigabyte we see here. And if of course, I can then if I browse this, evaluate the table, you get a really nice representation of the table here, where I can scroll to the right, and I can scroll to all the records that are contained in this table. What are the operations that you can do on tabulars? I can, for example, inspect the schema, where the schema gives me information about the actual representation that is used in memory. I can use, for example, extract rows using the regular syntax that you know from lists and from data sets. Like, for example, giving the first, okay, just extract the first row, please. And using the normal function will then, of course, convert this row to a regular association. I can extract a range of values using the span syntax. That is also all very regular Mathematica syntax, which works as you expect on tabulars. I can also extract a column, and this column will give me actually a very dense column representation of this column here. And for another interesting feature is that I can extract tabular data as another expression type, like, for example, columns and rows, or even matrices, data sets, and time series. For example, to extract all the columns at the same time, I can use this from tabular and use the columns option here. But I could also use, for example, if I want to use, for example, this latitude and longitude, if I want to extract this data as a time series, I can use this from tabular and give it the type time series, and then specify where the time column and the value columns are to be taken from. This will create then a time series object, and this time series object can then be further processed using the very comprehensive time series processing machinery that the Wolfram language gives you. Of course, we also may have to clean up tabular data. For example, let's just look at the first 10 numbers. We know that in the Wolfram language, we have a neat representation of geolocations, which is called geoposition. Geoposition is actually a symbol built into the language. And for example, for cleaning up, what I really want to do is I want to get rid of these two columns here and replace them with a Wolfram language geoposition. I can do this with the transform columns table, and say, please transform the geolocation, at least add a new column called geolocation, and give it the geoposition of latitude and longitude. And at the same time, please delete the latitude and longitude columns from a tabular by setting them to nothing. If I do that, it runs, and you see it gives me a new tabular where we see on this the actual longitude and latitude has been replaced by a geoposition expression. If I inspect the tabular structure now, you see that interestingly, this geolocation is now stored as a so-called inert expression, which means that tabulars can also store regular mathematical expressions, which are called inert expressions in the context of tabular, because they are actually Wolfram compiled compressions. Let me use this. For example, let's say you want to do a select on the tabular. You can do this. Let's select all the rows meeting criteria, like all the provinces, all the post offices which are in Ontario. I can do this with a select function here. I can use the aggregate row function to group records by a key and compute a summary for each group. Like I'm doing this here. This gives me, for example, all the post offices in the different provinces shown here. Or I can even use the pivot table command, which is a new command, to create the pivot table, which has which uses different indices for the X and the Y axis, like for example the province and the city type, and the actual elements will be the number of postal offices in the respective category. So here, for example, I then have this shows me for each province and for each postal code which city type has the number of offices shown here. We can also do visualization based on tabular data. Like, for example, we have this geolocation data in the tabular, and that we use let's just extract the geolocation column from the data that I have. I want to visualize the geolocation of all the post offices in the provinces of Alberta. And here I extract the data, which is specified as a table column. I have now I'm transferring this to a geoposition because the geographics needs this data to be in the form of geoposition. This will give me will wrap all the number of points in the geoposition. And I can then use the geographics to visualize the actual location of the post offices on a map. Okay, it has to download some information from the web first. Yeah, and when it's done, you see, yes, let me just blow this up a little bit. You see that it now shows the location of these post offices in the province of Alberta, Canada. And you see, with very little operations and very little code, you can do a lot of transformations. And the great thing about it, it lets you work with data on a very high level with actually going into the details of each record. And the great thing also is it works very well for larger amounts of data now, something which was not doable before version 4, was much more difficult to do before version 14.2. I mentioned that tabular also features out-of-core data. How does this work? For example, if you have a SQLite database file, which is, for example, this example database file that comes with Mathematica, I can then use a tabular and say this is a relational database, and I want to import the offices table from this database. It will then use SQL commands to communicate with this database. And if I run a select, for example, on this out-of-core table now, the actual select is run in the database and not in the Mathematica session. And using toMemory now, I can then bring just the result of this select command into my session. This is very useful if you work with terabytes of data, where, like, for example, of course it works with all databases that are supported by Mathematica, like, for example, Oracle databases, SQLite databases, Postgres databases, MySQL databases. And this is really great for doing a rough filtering of the set before you're using toMemory in order to load the data into your Mathematica session. Finally, let's look at a new feature which is called GPU computation. This has just been the first step into a lot of computation, which uses the Wolfram compiler in order to do GPU computation. There's now this new GPU array command which lets you represent data which is actually stored in the GPU, because you probably know that GPUs have their own memory, and they don't have to use the main memory of your computer. They have their own memory, and that means in order to run operations on that on data, you have to bring it to the GPU memory first. And with GPU array, you can do that. You can and many built-in functions such as linear, solve, plus, part, and other ones are active already running on the GPU. That means, like, for example, these functions here, like sin, real, abs, FUR, min, max, and so on. If I run these are actually run on the GPU inside my notebook. And as you see that the resulting result of these functions is actually a GPU again, which is stored in the GPU memory of the machine. And this gives you a nice speed up. For example, if I do this complex vector operation where I'm squaring a vector and doing some more transformation here, and if you compare this performance with a regular vector which is run on the CPU, you see that that the GPU version on my not very efficient GPU that I have on my notebook here is already faster than the one I have if I do it as if I do it with the CPU. And this is only the beginning of a long journey where a lot of functionality will be added. And this is all made possible by the Wolfram compiler, which is able to generate code for different GPU architectures and different CPU architectures without bothering the user. Yeah, if you want to learn about other features, I have collected a summary of links which you might find interesting. Therefore, there's of course this a reference of the summary of the new language features, which is always released with each new version. And there's also Stephen Wolfram always releases a very comprehensive blog post where he introduces all the highlights of the new version. And of course, there are also YouTube presentations. There's usually the one from Stephen Wolfram himself. And what I also always find very interesting are the John McClune based presentations on the new versions, which I have added here as well. Yeah, we are running out of time anyway, so thank you for your attention. And if there are any questions on the new versions or other things, please, we can have a discussion now.